Let's start with a few math basics and terms that are necessary when working with water operations and calculations. This material will be reviewed for some viewers, so we'll move through it fairly quickly. For example, power's notation is really just a shorthand way to show multiplication. 4 times 4 can be expressed as 4 to the second power, or 4 squared. 4 to the third power, or 4 cubed, is 4 times 4 times 4. Scientific notation is a method by which any number can be expressed as a term multiplied by a power of 10. Examples of numbers written in scientific notation are 5.4 times 10 to the power of 1 and 1.2 times 10 cubed. The numbers can be taken out of scientific notation by performing the indicated multiplication, such as 1.2 times 10 times 10 times 10, which equals 1,200. An easier way to take a number out of scientific notation is by moving the decimal point the number of places indicated by the exponent. A positive exponent indicates a decimal point move to the right, as we just saw. A negative exponent indicates a decimal point move to the left. Dimensional analysis is a tool used to determine whether a math problem has been set up correctly, by working only with the dimensions or units of measure and not the numbers themselves. To use dimensional analysis, you must know how to express a horizontal fraction as a vertical fraction, how to divide by a fraction, and how to divide out or cancel terms in the numerator and denominator of a fraction. When a problem involves division by a fraction, the rule is to invert the numerator and denominator of the fraction being divided, and then multiply. For every term canceled in the numerator of a fraction, a similar term must be canceled in the denominator. Dimensional analysis is used to determine if a particular formula uses multiplication or division, and if the equation will provide you an answer in the desired unit. Let's try dimensional analysis in the following problem. The flow rate in a water line is 2.3 cubic feet per second. What is the flow rate expressed as gallons per minute? Now let's check the math setup. By converting the problem to a vertical formula and by canceling similar terms, you can see that the answer will ultimately be in gallons per minute. Getting the desired units indicates that you've probably set up the problem correctly. Another method for checking your work before you get too far into a calculation is by rounding and estimating. If you round the numbers and estimate, you can do a quick calculation to make sure your specific or detailed answer makes sense. You'd be surprised how many mistakes occur simply when multiplying, dividing, or punching the wrong button on a calculator. Rounding means replacing the final digits of a number with zeros, thus expressing the number as tens, hundreds, thousands, or tenths, hundredths, and so on. When rounding whole numbers, if the digit is less than 5, replace all digits to the right of the rounding place with zeros. If the digit to the right of that place is 5 or greater, increase the digit in the rounding place by 1 and replace all digits to the right of the increase with zeros. When estimating the answer to a problem, round each number in the calculation so that only one digit remains, with the rest of the digits in the number either changed to zeros or dropped in accordance with the rounding rules. You can add the number of zeros back to your answer after your quick math to get an appropriate estimation. In this way, the estimation can often be done in your head, or at least with a minimum of computing with a pencil or calculator. In treatment plant operations, we use equations for calculations such as the detention time of a tank, flow rate in a channel, filter loading rate, or chlorine dosage. But to make these calculations, we need to know the values for all but one of the terms of the equation used. For example, let's look at flow rate. We know that the equation is flow rate equals area times velocity. To solve this puzzle, we need to know two of the values. When solving unknown values, most of the equations we use in water operations involve multiplication and division. From time to time, we also encounter equations with addition and subtraction. In the case of multiplication and division, you must rearrange the terms so that x, the unknown value, is by itself. A good rule to remember is that anything done to both sides of the equation does not change the equation. Move x to the top or numerator of the fraction if it's not already there. Move any other terms away from x to the other side of the equal sign so that x stands alone. To move a term from one side of the equation to the other, move from the top of one side to the bottom of the other, or from the bottom of one side to the top of the other side. This is called the rearrangement rule. Now let's look at equations involving addition and subtraction, such as might be used when calculating chlorine dosages. The rule here is to rearrange the terms so that x is positive and by itself. However, since there isn't a numerator or denominator, you can't crisscross terms. Instead, you move it from one side of the equation to the other. As you do, you must change the sign of the term, if positive to negative, if negative to positive. If there is no sign in front of the number, assume it is positive. Once you have ensured that the unknown value is a positive and by itself, you can solve the equation. Here's how this type of equation is used at a treatment facility. Chlorine dosage equals chlorine demand plus chlorine residual. If you know that chlorine dosage is 7 milligrams per liter and chlorine residual is 0.2 milligrams per liter, then we can determine that chlorine demand, the unknown value, must be 6.8 milligrams per liter. A ratio is the relationship between two numbers and may be written using a colon or as a fraction. When the relationship between two numbers in a ratio is the same as between two other numbers in another ratio, they are said to be in proportion. A method used to determine if the ratios are proportionate is to cross-multiply. If the answers are the same when numbers diagonally across from each other are multiplied, then the ratios are proportionate. Sometimes only 3 of the 4 numbers in a proportion are known. It is possible to determine the unknown value by solving the rest of the equation as shown here. In practical application problems, the ratios will not be arranged as in the previous example. You must know how to set up the proportion before you can solve the unknown value. Since a proportion establishes a simple relation between two ratios, if any number in one of the ratios changes, then another must also change to maintain equality. In many treatment plant operations, a change in one operating condition produces a proportionate change in some other condition. For example, changing the speed of a metering pump changes the quantity metered, or changing the amount of chemical added to a certain volume of water changes the strength of the solution. If you establish a relation or ratio for a particular condition, then when one of the quantities changes, you can calculate what the new value of the other quantity will be. To set up a proportion, first analyze the problem to decide what is the unknown. Then decide whether you would expect the unknown value to be larger or smaller than the known value of the same unit. Write all values, including the unknown factor, in fraction form, grouping values having the same units, such as pounds and pounds, time with time. Also, be sure to put the smaller value in the numerator or top of each fraction, and the larger value in the denominator. You will need to follow these 3 rules. First, if the unknown is expected to be smaller than the known value, put an x in the numerator of the first fraction, and put the known value of the same unit in the denominator. The second rule is that if the unknown is expected to be larger than the known value, put an x in the denominator of the first fraction, and put the known value of the same unit in the numerator. And finally, make the 2 remaining values of the problem into the second fraction with the smaller value in the numerator and the larger in the denominator. Let's put these rules into an actual water treatment problem. If 5 pounds of chemical are mixed with 2,000 gallons of water to obtain a desired solution, how many pounds of chemical would be mixed with 10,000 gallons of water to obtain a solution of the same concentration? The unknown is the number of pounds of chemical. You would expect the more water used, the more chemical would be needed, so the unknown number of pounds, or x in our equation, will be the denominator, and the formula would look like this. It's then possible to solve the unknown value, with the answer of 25 pounds. Here's another problem, and you can pause the video to work on it if you like. A pump working at 86% efficiency can fill a certain tank in 49 minutes. How long will it take the pump to fill the tank if the pump's efficiency is only 59%? The unknown value is the time it takes the pump to fill the tank at a reduced efficiency, and we would expect the unknown number of minutes to be larger than the known number of 49 minutes. The known values of the other unit are 59% and 86%, so we arrange these numbers into a fraction by which to multiply 49 minutes. The answer should be larger than 49 minutes, so the fraction should be larger than 1. 86 over 59. We can now determine x by multiplying 86 times 49 and then dividing it by 59. The answer is 71 minutes.